All right, so if you haven't noticed, I don't teach off slides. I created the slides for you guys, for the students, but I don't teach off of them. So I want you to understand the concept, not the flow of some slideology. All right, so you'll see, I'm going to kind of bounce around on some things. All right, so today's whole point is vectors and phasors, right, and understanding kind of how power applies to vectors and phasors. We talked about some of the basic math behind it, right? But we need to make sure that we understand all those previous units in order to understand why what's happening is what's happening. So I want to do some demonstration to kind of make sense of some things. Okay. So if I come up over here, let me get somebody. Reed, come here. You can be my lab partner. Really, I just need you to back me up and get me juice boxes. Anybody know what movie that is? Kicking and Screaming. You guys don't watch Will Ferrell? Marginally achieved core standards. Okay. All right. You just, and it's not Step Brothers. It's marginally achieved. I mean, it's Kicking and Screaming. Coffee's the lifeblood that fuels the dreams of champions. Good quote. All right. So I'm going to set up a simple resistive circuit. Obviously, you've seen by now I've set some stuff up here on the board on my computer so that you guys can see what we're doing. But I want you to kind of understand, as I do things on here, what's going to happen up here, right? What's going to happen between oscilloscopes, within gauges, within phasors, right? Because that's what this is all about, all right? So I want to set up a simple resistive circuit, okay? I'm going to set up a circuit that is, this is what I'm going to do. I'm just making things up here. So I'm going to go that, and I'm going to say 120, what are we at, Fortini? 124.8, sure, okay. And right here I'm going to say 171 ohms, which is the equivalent resistance of what three resistors?
All of them. 300, 600, and 1200.
300, 600, 1200, right? 171 ohms, okay? Then I'm going to put that there. Like that, okay? And we're going to display everything, all right? Everything that we've learned. Because I know when we did the first one, did we look at the oscilloscope on the first, or day two? We started looking at the oscilloscope, right? I think. I don't know. We'll see. No, we did, because we saw that they were in phase. You just really didn't know what that meant at that point, so maybe it wasn't really applicable. All right, so here's what I'm going to do. I'm going to set this up, okay? Now, bear with me. I don't do the concept of plus, minus, right? I just go, all right? So bear with me here. I'm going to go from this power source here into my meter, because we hook up our amp meters how? Series or parallel?
Parallel.
What? Who said parallel? Who said parallel?
Village.
What? Gold star removed. You got to work back up now, buddy. All right, so what I just set up is the current metering and the resistor in the circuit, right? All right, now I'm going to flip these switches, all three of these, because the equivalent resistance of a 1200, 600, and 300 ohm resistor comes out to 171 ohms, right? We know that. Now, give me a red one, please. All right, so now I'm just going to meter the voltage across my one piece of the load. All right, now I hook up my voltmeters in how? Series, parallel? Gullage.
Parallel.
Boom, gold star's back. That's like a half a star, though, because that was really basic. Because it wasn't linear, right? By missing the first one, that's like -2. So you're like negative 0.5 or something, like -1. I don't know. All right, so I'm going to go to E1 now. I'm going to pop it across here. Now, does it matter if I pop it across here or here? Not in the context of this, right? Nodally, it's all same reference points, right? Okay. So I got E1, I1. Yep, good. Okay. So let's talk about what we should expect. All right. Well, if I have a purely resistive circuit, right, and I have 124 points, what do we say? 124.8 volts, and I've got 171 ohms of load, what should be my current going through the circuit? Calculators, when I say what should be the current, that's indicative of you grab your calculators and calculate it out, please.
0.9. Yeah, 4.9. 124.8.
0.73?
Amps.
Yeah, what were y'all talking about?
So we all in agreement of that?
Yes.
Yeah? Okay. And also, just an additional step, if we were to calculate the apparent power of that one, what would be the apparent power of this circuit?
127.
What is it? This is what.
91.1.
What is it?
91.1.
Now, how do we get that?
E times I.
What is it?
91.1.
Whatever. Okay. All right. So that's one way of doing it, right? Or you could have used what? You just calculated the current, so you could have done I squared R. You could have done the 0.73 amp squared times 171 ohms. Does that come out to be the same? 91? Check. Tell me.
Yes.
Is it the same?
Yes.
Yes? Cool. So we could have done either one, right? All right, so that's the apparent power. What is my real power consumed in this circuit?
It's the same on this.
What?
It's the same on this. There's no reactive power.
There's no reactive power? So what's the phase angle between current and voltage? There isn't one? So that means it's in phase, right?
Yes.
So then if we were to pop this circuit up on the oscilloscope, we should be able to see that they rise and fall, they peak, they start, they zero, same point, right?
Yes.
And what our meters should indicate all this math we did. Cool. All right, so where are we at? We got 123.4, so we're going to be slightly off. So I've got E1, I1. We're at 123 and 0.72. What do we say? 0.7. Yep. Cool. All right, so now I'm going to say, I think I already got the P set up here. We're at, it's showing negative value because of how I wired it up, but the 90, we're roughly about 90. What do we calculate?
91.
Cool. All right. So, ooh, my polarity's off right there. What do I got here?
Huh.
Let's see which one is out of phase. Do you see what? Now, how did I know that was off?
Because they were opposite.
'Cause
They were
what?
180 degrees out of phase.
But how? I mean, like, we know that resistance should be in phase, right?
You had your voltmeter backwards.
Yeah. So now, I just visually looked, just from understanding the circuit, and realized something was wrong, right? See that? Okay. That's why sometimes looking at the oscilloscopes, looking at these diagrams, you can deduce things if you understand a system. You wouldn't know anything about that if you didn't think into the system. Okay, so we've got this. We see no phase angle difference here, correct? Now we look at our phasor diagram. Now the length of that phasor, that vector, all right, is what? What does the length indicate?
The value
Directly
of
correlates
that.
to the value.
To the value, right? To the peak of that sine wave, right? To the magnitude of the sine wave. So and right now we're seeing that the current vector is laid completely on top of the voltage vector, right? And that is because why? They're in phase. There's no angular difference between the current and the voltage, correct? Okay, so now based on the proportionalities that we know between Ohm's law, if I dial down the voltage, we're going to see what happened to this voltage vector.
Shorten.
It's going to shorten. What's going to happen to the current vector?
Shorten.
Cool, let's see if this works. Boom. Now look what's happening over there on that oscilloscope at the exact same time. We're staying, the same angular relationship exists. All right? All this is the same. We're keeping the frequency. We're not adjusting the frequency. I mean, it's 60 hertz from the power supply, but now we're seeing these differences, right? Cool story. All right. Okay, cool. Now, give me some more leads, please. Let me get some red ones here.
Job, Reed.
Listen, you're doing awesome. You're a great hand model. All right. So now what I'm going to do, or what I did, is I drew in a capacitor and I drew in an inductor, right? I still got a metering circuit in there, but essentially that's what I did. I just put them in parallel. I'm just adding them to the circuit. What I'm going to do right now to demonstrate this, though, is I'm going to open a switch here, here, and we're just going to look at the inductor. So let me close these. All right. We're dialed down, and we'll turn this up right here. I'll do one right here. Okay, so understanding the angular differences between voltage and current with inductive circuits, what is the angular difference between voltage and current? What is it? 90 degrees. Inductive, yes. 90 degrees? 90 degrees. Okay, so that means if I have nothing but inductance, is it exactly 90?
No. No, because
we're gonna have a little power triangle here. It's minute, very minute, but you're gonna have a little power triangle here. But for all intents and purposes, we'll say 90. Okay. So that means if I just hook up just an inductor and I do this exact same exercise, where is the current going to be in reference to the voltage? 90 degrees off. Which one's going to be leading which?
Current leads. Voltage leads current. Yeah.
Voltage leads current? All right, so now what's happening? I'm dialing up and dialing down, right? But we're seeing the same magnitude variation, so that science remained consistent. What we're seeing now with these vectors is, it's hard to look at this, and I mean, you could do the time-based thing here and multiply times 360 and divided by the period. That's kind of complex, right? It's a lot easier to look over here and understand that 80-something per, 85, 86 degree offset of the inductor right there? Yeah?
Yep.
Okay, so now, this is my voltage vector. This is my current vector, and we said voltage is leading the current, right? That's Eli of Eli ice. All right, now what if I go over to my phasor diagram here, and up here at the top, I can set what my reference is. Now I'm going to set current as the reference. This goes back to what we talked about yesterday, right? Like, is there a difference in the relationship?
No.
It's still leading by 90, right? All I'm doing is switching what my reference vector is, correct? That 90-degree relationship and which one is leading versus lagging is consistent, correct? Okay. All right, so we demonstrated that. So now I'm going to go, I'll leave it like this, okay? I'm going to turn off, let's dial it down. And again, notice here, we see over here that this is peaking before this one, right? So that voltage is leading, okay? Voltage leading current, inductive circuit. So now I'm going to switch. All right, now which one's peaking first?
Current.
Current's peaking first. Why? Because that's the ice. That's the Eli ice, right? In a capacitive circuit, current's leading the voltage. Okay, so now what's happening? Notice on here now, we're getting a perfect 90-degree angular relationship there, correct?
Yes.
Perfectly 90. Notice on the inductor, it wasn't perfectly 90. That's going to kind of play into a part here in a minute when I show you something, okay? All right, so if I do the same thing here, dial up, dial down, right? It is what it is, okay? All right, this is simple enough, and we can use these Ohm's law. We learned that we could do the capacitive reactance and the inductive reactance. Those give us an ohmic value. They're a complex number, okay, which means it's that J, right? And we can solve for what the current should be. All right, so right now in this circuit, I've got, what do I got there? It's the equivalent of, which one is on? That's a good question. All right, I got the equivalent capacitance. The capacitive reactance is 300 ohms. All right, so then what should be my current?
Right now?
Sure, right now, 105.2 volts.
300 ohms?
Yeah, 300 ohms.
What?
He had a question.
Did you say 300 amps? Oh.
0.35.
0.35? What are we seeing up there on I1?
0.37.
0.37, so we're right in that ballpark, right? There's some rounding conventions and stuff going on. Cool. All right, so we see these relationships here, and we can see them happening here, and this is, if you're looking at these simple little things right here, you're like, I see some validity there, but I could just as easily look at the oscilloscope and see the same thing, right? Cool? All right. Now, what I want to do is I'm going to go back to resistance. I'm going to pop this up. Let's turn up our magnitude so we can see some cool stuff. Now I'm going to kind of go to reality and say, well, what if we actually had inductance? Because inductance is occurring. It's a natural phenomenon out there with alternating current, right? It's happening. So I'm going to flip, that's a capacitor. I'm going to flip inductance and see what happens now. All right, so now we're at a totally different angle. We haven't seen this angle before, right? We're seeing a completely different angle going on. That angle, now back to the kid scenario in the store. You got a kid pulling you this way, kid pulling you this way, kid pulling you this way. In this case, we got a kid pulling us this way and a kid pulling us this way, so we're going to kind of gravitate this way, right? We talked about that yesterday with vector math, right? You take the head, tail, put them together, draw the other vector. You know, it's kind of simple enough. But I want you to kind of understand what the end state is that you're seeing what is the result from these different forces. You remember those math problems in school where you're going across a river and the river's flowing this way and you're going at this speed and the river's flowing this speed and they want to say, well, how do you end up over here? Where are you going to end up?
Downstream.
Right? Yeah, where are you going to end up? Well, that's a math question, right? That's a similar concept, Pythagorean theorem. Way to read into that. Good though. All right. Okay. So now
That would just use logical ideas here.
let's look at that. Let's look at that. The current vector. All right. And I see how long it is. Now I induce some inductance, and what's happened to that current vector?
Shortened it.
When I put some inductance in,
It got longer.
it got longer, right? I increased the magnitude. I increased the current that's going into the circuit. All right. So when we start talking about, well, let me back up. You saw that. Put a pin in that. Okay. So now I'm going to add, actually this is going to decrease the inductance because I'm going to put some switches here. All right. So you see what we got going on? I got some inductors in here. I got my resistor in here. And based on this, I'm sitting somewhere we can assume that's about a 50-degree angle. Would we agree? Ish.
51.06.
Sure.
It says on the bottom.
Absolutely. Look, we're reading. Cool. Okay. So now, right now, I have 300 and 600. Oh, you can go ahead and sit down. You're doing a really good job, though. You get a gold star. Gold star. All right. So now, we said that inductance and capacitance, again, they're kids pulling in different directions, right? Capacitance is pulling in a complete 180 degree out from inductance. So if I was to add some capacitance to this circuit, what's going to happen? What's going to happen to this angle, do we think?
Closer to increase.
What?
It's gonna increase.
It's going to increase?
Closer to 90.
Closer to 90?
Depends on how much you add.
You're adding reactance.
Let's question. I'm asking.
It depends on how much you add.
So I've got some resistance in there and I got some capacitance, and that's my resultant is somewhere in between the two. Yeah, yeah? All right. Now I want to add some capacitance. Okay? Where is my phasor going to, what direction is it going to go by adding some capacitance? So you're saying towards 90. What did you say, Dewey? Towards 0? What do you say?
Or zero.
0? Huh? Because Dewey did? They saw this demonstration yesterday, so they should be saying it because they saw it yesterday. All right? All right, so I'm going to add this. Oh, what happened? Wait. Oh. Okay. So by adding some capacitance, I said it was the kid pulling in the opposite direction, right? So again, this is like being at the store. Originally, I just had the one kid, and we're doing this, and you still got your weird kid with the leash, right? And then I'm adding another kid over here, who's pulling you over here. Now, based on this, he's not pulling a whole lot, right? He just pulled a little. And based on my switches over here, let me see what I got, okay? So I got 2 inductive switches over here, 1 capacitive switch over here, okay? So what if I flip the same amount of capacitance, some capacitive reactance, as I have inductive reactance in this circuit? It's going to what?
Yeah, 0.
Closer to 0?
Yeah.
All right, and watch what that current vector is going to do too. All right, so now we're not perfectly at 0. Why are we not perfectly at 0? I got the same amount of capacitance as I do inductance when it comes to reactance. Well, resistance is pulling this way. What is this little bit? What's that little bit offset?
It's like the impedance in all the wires and stuff.
The resistance in the inductance is creating a little bit of active power there. All right, you're not getting that perfect 90-degree offset. You're getting a little bit off. So when you induce those same amount of values in there, that's why you're seeing that slight little variation right there. Just in an ideal inductor capacitor situation, when you say ideal, they're just saying that negating all those little sciencey things like the resistance in the inductor, it would be perfectly 90. And then the theory would be then that if you induce the same amount of capacitive reactance as inductant reactance, you're going to minimize the current vector, right? It's going to decrease, and it's going to come back to what we call unity, where there's should be 0 phase angle between current and voltage, and that would be a perfect scenario. Perfect scenario, yes.
Sure. So if we was to relate, you had the 3 kids, one pulling each direction, and then the one with the leash pulling forward. How would you relate the capacitive, inductive, and resistive load with those kids? I'm just trying to.
So the capacitive and the capacitive reactance and the inductive reactance are the two kids pulling this way, when in fact the inductive reactance is really a little bit off this way. He sees like a squirrel over there, so he's like wants to go this way, but he sees this little thing here too. And the capacitive one's just straight beeline, 90 degrees out. Weird kid with the leash resistance, straightforward. Okay. All right, cool. So we see that we are almost perfectly in unity right now. There is almost a 0-degree phase angle between current and voltage, which now when we go back to our trigonometry functions there, we know that if cosine of 0, what is the cosine of 0? This is why I say use your calculator. 1. All right? 1. All right? What? God almighty. All right. In reality, okay, we're seeing this up here. What do we got? 2 degrees there? 2.5 degrees? Yeah. What's the cosine of 2.5? You can put negative 2.5. It's cool. What is it? 0.99999?
Yeah.
So in reality, your power factor is a 0.99999 power factor right there, which means you do have some slight inefficiency there, but you're almost getting perfect, right? And that's how this power factor plays into this, okay? All right. So all right. Sections 5.2 and 5.3 are really going to dissect some stuff that's going to be the variance between series circuits and parallel circuits. And then 5.4 is going to get into impedance, but I kind of want to wrap all of those up together. There's some different things that occur mathematically and vectorially between parallel circuits and series circuits when it comes to these different capacitive and inductive reactances and how they relate to the resistance. We talked about impedance before, correct? And you guys talked about that yesterday, right? What is impedance?
It's a combination.
It's what?
It's the combination of the opposition flow. It's like all three.
All three of them, right? The total opposition to current when taking into account everything, right? All right. So in a series circuit, let me rewire this real quick. And I'm going to do just resistors and capacitors. You've seen how I had them right here. These are, these were in parallel. But I actually want to make them in series. I almost need my little lab helper again. I don't want you to have to get up. Oh, let me inconvenience you, Reed.
I got you.
You got me? All right, so I'm going to take that to there. And then bring this up to, oh, I'm so close. All right, now I'm going to read E1 across my resistor. Do I still got 2 in my hand? I do. Okay, now I'm going to read E2 across my inductor. Oh, man, I keep coming up short. All right, so here, well, that's not a good color. This is what I'm trying to hook up. All right, and then of course I got this over here. And this over here. Okay. And then I got I1 reading the source. Okay. So if these were resistors, just resistors, and we wanted to figure out what the current in that circuit was, how do we do it? I'd add the resistors because then that would give us the equivalent resistance, right? Okay. And then what? And then divide that from the volts. Okay. All right. Well, in what we're going to call this an RL circuit, you hear RL circuit, RC circuit, RLC circuit. That just means whether it's resistive, inductive, capacitive, what things are all in that circuit, right? In this RL circuit, this is going to be out of phase with this, right? We don't just add those things up. One is going to be some value, and the other one is going to be an ohmic value, but it's going to be orthogonal to it, either positive or negative direction. And it's going to have a complex number associated with it. That's that little J, okay? So let's say that this is 100. We want resistance R1 is 100 ohms. And we're going to say that L1, the equivalent inductance, is going to be 100 ohms. All right? And so I'm going to say J 100 ohms here. So now, how do we go about solving it? I mean, when it was just resistance, it was easy, right? We just added them up. How do we do it now? Do what? What do we got to figure out? We just talked about it a second ago. What do we got to solve for? Impedance. Impedance. Because if I was to vectorially represent this right here, I should see currents that are 90 degrees out of phase from one another. Correct? Or about 80 something degrees out of phase from one another. Going through there. Or voltages, I should say, in this case. Hmm?
Plus or minus JX.
Plus what?
Plus or minus
R plus or minus
JX equals
100 minus.
I'm hearing all kinds of things. Okay.
For series, it's a plus.
For series, okay? In a series circuit, solving for impedance, which is represented by the Z, all right, we're just going to use Pythagorean's theorem, okay? We're going to use Pythagorean's theorem to determine, because that's a triangle, they're orthogonal, right? In an ideal inductive situation, they're perfectly 90 degrees out, all right? So we can use the regular Pythagorean's theorem here, and we can say that Z should equal the square root of R squared plus X sub, I always want to write the C, X sub L squared. Am I right there? We good? We tracking? Okay, so what is Z? Hmm?
141.
If you used your calculator, you would have got 100. Did you use your calculator?
141.42.
What?
141.
141. Okay? The hypotenuse is, I mean, you got an A side and a B side. The hypotenuse has to be something larger. All right, so Z equals what? 141? All right, Z equals 141 ohms. Okay? Now, that's going to be the magnitude of our vector, but what direction is that resultant vector going to be in? What's that phase angle going to be? Okay? Now we're going back to the trig piece of this. Okay? Now, again, you can solve this in a couple different ways. The book's going to have you use the arctan. Okay? We're going to use the arctan, all right, of the reactance over the resistance. Okay? The opposite over the adjacent. The y component over the x component. All right? So, what is the phase angle that this vector should be at? What is it? 89.5? Okay, let's see. I'm going to do the math over here. So if tangent to the negative 1 of x sub L over R equals theta, then I get tan negative 1 of 141 ohms over 100 ohms equals, is that what we got? What is it?
54.6.
54 point. Yeah. Where am I at? Okay. Okay, so that means by this convention here, all right, with an RL circuit and what?
So we're finding the phase angle of
The impedance.
Z.
The impedance. We're just looking at the phase angle of that resultant impedance. Okay, which this all in turn, you're going to see that it's going to be circular. You're going to see this translate into the currents, also in the voltages too. It's because of the proportionality stuff that's going on inside of these circuits. All right, so I just want to show you that, and then let's turn it on and see where we're going to be. Okay, so I've got 100 and 100, and if I remember this correctly, in order to get 100 ohms, I should have picked an easier value. In order to get 100 ohms here, I need to go 3 of these in parallel with the 300 ohm resistor. Is that right? Anybody? What's... Yes? All right.
Just need 2 banks.
Do what?
1, 3, 4, 5, and 6.
Yeah. And then to get the same inductance value, I believe we should be doing the same thing. Are we okay? We tracking?
Yes.
Good? Okay. All right. See that? So I got 0.8 Henrys, 3 of them in parallel. Let's confirm our numbers. So 1 over L EQ equals 1 over 0.8 plus 1 over 0.8 plus 1 over 0.8. What does that equal? What is it? 0.27 Henrys. So now if I want to know X of L, it equals 2 pi 60 times 0.27 Henrys. What's that?
100.5.
What?
100.5.
Okay, so we're at that 100 level. Right? That's what we were looking for, right? I was just figuring out which one of these. I'm just showing you through the exercise how we're going to figure this out. Okay, so based on all of that, all right, let's turn on our power. Oh, our power's already on. Look at that. Okay. All right, now, ooh, I should have some current. What do I not have hooked up right? Let's see, we're going over to here, here to here, here to here. That's up, up. Okay, yeah, I'm reading it. Why is it? Oh, it's right on top of it. Magnitude-wise, my E1 is now just going that, and I'm not showing my source. So right now I'm just looking at the voltage across the resistor, which is that one. Yep. And then E2 is my voltage across the inductor, which let me turn these on so we can see them. And based on that, I can see that I need to. There we go, and that is E2 voltage leading. Yep, and we have E1, E2, and let me turn that back on. Did I hook up I2? Well, it's in a series, so it's going to be the same. Okay, all right. Now I'm going to hook up one more channel, which I'm going to hook up channel 3, and bring that back to the source. Okay, so we're also seeing source voltage. Let's take a look there, though. I see E1 and I see E2. Yeah, yeah?
Yes.
And what are those each reading?
85.
They're reading what? 80, 85? So that's a series circuit, so those voltage drops should be the same across each one? I mean, they should sum up. That's Kirchhoff's voltage law. They should sum to the source. Does that mean our source should be 160 in this case, or 165? Should it? Hmm. Yeah. Yeah. What are we seeing? Talk to me. What are we seeing? What is our source voltage? 124. Okay. Now, somebody explain to me why those voltages aren't summing to that 124. What? Anybody?
You're losing some to
The voltage, the voltage shift, the angular difference between the voltage and current across the resistor is what in compared to the voltage and current relationship across the inductor? The inductor. Are they in phase with one another? There's going to be a 90-degree offset there, right? So now you're seeing the results of vectorial differences here between two being out of phase from one another. Okay? So right now, all right, I have reference as I1. This is a series circuit. In a series circuit, the current flowing through, right? It's the same, so we use that current as the reference. So now I'm just looking at the varying degrees of the voltage vectors. All right? And I'm seeing that one is here and one is up here. All right? There's a 90-degree shift, well, 88 point something degree shift, right, between the voltage across that inductor and the current going through the inductor. And there is a 0-degree phase shift between the voltage and current going through that resistor. So now, going back to what you said yesterday with the vector math, I'm just looking at these two vectors here, this one and this one, which blue, that's E2, that's going across the inductor, right? Red one here, it's kind of hard to see because both those colors are right there on top of each other and their magnitudes look like they're almost the same in scale up here, but they're right there and right there. Now, if I move this line over to here, and then I draw the line connecting, what am I left with? I'm left with a hypotenuse, if you will, right? That varying value right there, all right, is why you're seeing that. That's why you're seeing that those voltages aren't additive. Does that make sense? We're confused?
the hypotenuse was the apparent power, right?
Do what? No. Don't fixate on the power triangle as just the hypotenuse and the opposite. It relates to everything, because now when we're talking about just current and voltage, that also creates a triangle in these capacitive and inductive circuits. We can also talk about impedance and just resistance and reactance, because it's orthogonal, creates a triangle. Okay, so don't fixate on the hypotenuse being that. The hypotenuse of whatever triangle you're creating with vectors is the resultant vector. All right, so when you have two vectors, call them what you want. And you're going to do this in the lab too. You're going to do this with current. You're going to do it with resistance. You're going to do it with the apparent power, the Q. You're going to do it with all this stuff as it progresses, right? So just remember that resultant vector, that hypotenuse, is just the sum of two forces pulling you in other directions. Okay? Just the sum. All right? And where's our, we see our phase here. We're at 43 something there on the voltage, and that's for some other varying reasons, but the important thing to kind of understand there is those two things are not summing like they did in a regular circuit. There's angular orthogonal differences in the relationship between that inductance and that resistor that's causing this. All right? So you're going to do this, something very similar to this in 5.1, I believe. All right? And you're not going to know why. You're not going to do any further math on it to kind of deduce some things. So I want to kind of give it all to you up front. So the current going through our circuit here is the 0.8, all right? And what do we have over here? We got 120. What do we got? 120. 124, right? And we said that our impedance was what? What was it? 141. Did we do that math somewhere else? I thought we did the math right here. Did I draw that here? All right, so what is the 124 divided by the 141?
0.73.
What was it?
188.
What is it? 0.88. You guys probably ran the calculator. I wrote 171 right there. So 0.88. So what are we actually reading right there? 0.82, somewhere in that ballpark. So you're seeing where we're at though, right? Variations are off. It's kind of fluctuating a little bit, but you're seeing that current is at, scaled right there. That's where we should be, okay? Now, the difference, and I'll show you that here in a second, I'm going to set up a parallel circuit, and we're not going to use that same formula for impedance because just like in resistance and we see the relationship between equivalent resistance in circuits, we're using some inverses that are going on in there. Same thing applies to the impedance in a circuit, and so if we were going to solve for the same two things in an RL circuit that's parallel, we're going to use a different impedance formula, okay? And so I want you to denote that this impedance formula here is just for a series circuit, an RL circuit, or an RC circuit, or an RLC circuit for that matter, but one that's in series, okay? If it's in series, you're just using Pythagorean's theorem. Make sense?
Can you repeat that, sir?
If you are solving for the impedance of a series circuit, a series RL, RC, or RLC circuit, all right, you're going to use the Pythagorean theorem variant of this impedance. Does that make sense? I mean, it's just series circuit, and when I say series circuit, because you're going to be setting up some various ones today. This is one right here. This is an example. That might even be the same values. All right? When you set it up, when you solve for the impedance of it, you're just going to be using the Z equals the square root of R squared plus the resultant of whatever your reactances is squared. All right? So if you had a LC circuit or RLC circuit, and we added a capacitor in series with there, it would be, and you can see this in the formulas in your book, it's going to be the square root of R squared plus the quantity of X of L minus X of C squared. So the difference of those two, right? Kid pulling this way, whatever you're left with, squared, is going to equal your impedance. Okay? All right. So we just did all of that. We kind of confirmed it, and now we kind of see, too, these voltages here, right? Two different voltages. There's an angular difference between the two going across these loads, and now we're left with some resultant thereof. Okay? All right. So now I'm going to turn that off. Anybody have any questions with this? Are we good? Yes. Do you want to go into the parallel piece, or do you want to take a break?